Hi ladies and gentlemen, this is our third video on chapter 3, which is the root finding section of the text. And what we're going to do today is move into fixed point methods. This approach is different from what we have been doing, although there are tie-ins on the main themes to what we've seen with secant method and Newton's method. So let's just jump right in. Starting here in section 3.5, we see the definition for fixed point of a function. So we have a fixed point when, and you're familiar with this definition from before, I'm sure, when I have an input to my function g which produces an output that's equal to the input. And this is a common situation in applied mathematics. Addressing this type of function leads to a lot of the dynamics that we talk about, like fractals and Julia sets, Mandelbrot sets. Those types of things are based upon this recursive approach. So we've been using iteration, but this is a very specific type of iteration. This is recursion, where we take the output of our function and feed it back in as the input. So we've already seen this. This is what we wrote for Newton's method last time, and you'll notice we could really think about this in terms of, sorry about that, sometimes the tablet takes over. So we could really think about this is x to the n plus 1 is equal to some Newton's method function of xn, where the Newton's method function is of course defined to be exactly this. And then what we end up doing is we just have xn plus 2 is the Newton method's function applied to xn plus 1. This is recursion. All we're going to do with fixed point is work out this same type of approach, but we're going to do it in a different mathematical framework. So the first result here is straightforward, having to do with continuous functions on some closed interval. And I'll leave you to read that as well as look at the proof, which is the intermediate value theorem, and look at this example. What I want to do is get to one of the more important analysis theorems, and this is the contraction mapping theorem. So the contraction mapping theorem says that if we have a function and its derivative are continuous on some interval, and we have these two hypotheses, that the output values of the function are restricted to the same interval that the input values are coming from, and the rate of change of the function is less than 1, and we have some maximum value, that's what the k is, it's just the maximum rate of change of the function in the interval a to b, then we have a whole series of items here that are true. And I have provided the proofs for all of these. Remember, there are no proofs in this course. However, the reason I've included these, and I generally only include proofs when there's illumination to be found by going through them. So I recommend that you take a look at these proofs for the contraction mapping theorem. We'll come back and use some of the information in here in just a minute. So those are the conclusions, the 4 conclusions, and the resulting proofs. What I want to do is look then at how we use fixed point methods to solve problems when we're talking about nonlinear root finding. So the contraction mapping theorem provides us the ability to solve f of x equals 0. And how exactly does that work? Well, if I'm looking at the recursive function, g of x equals x. This is my goal. I'm looking for inputs that satisfy this. Those are the fixed points. Well, if I'm also looking for f of x equal to 0, then I can put these two ideas together. And what I have is g of x is equal to x plus f of x, because I can add 0 to both sides of my fixed point equation. Moreover, and this is an important point for us to be able to satisfy the conditions of the contraction mapping theorem, I'm interested in multiplying by some constant. Because of course, if I have an input value that makes f 0, then if I multiply by a constant, that's not going to change. I can multiply both sides of this equation by c, so I can multiply here, and I end up with this, and that's where the c comes from in my representation here for the contraction mapping. And now what I seek is I want a c value that allows me to meet the hypotheses that were stated in the contraction mapping theorem. And that's what this derivation right here is doing. Because what we need is we need to bound the magnitude of the rate of change of the g function by 1. We need something that's less than 1, because if we have that, then we have one of the powerful results in any mathematics, which is guaranteed success. What the contraction mapping theorem tells us is, if we can meet this condition for g, then we are guaranteed to have a fixed point, and more importantly, we are guaranteed to have a unique fixed point. So that's the motivation behind why we want this to happen. And what we want is for the rate of change to be close to 0. The question is why? Let's go back and look at the hypotheses for the contraction mapping and the results. So if we can find a rate of change that's near 0, and of course we prefer that to be near 0 across the entire interval, although in our case we need it near 0 at the fixed point, that's going to give me a small value of k. And what the third conclusion in the contraction mapping theorem tells me is that after n iterations of the recursive application of g, I am bounded between the fixed point and my approximation by this right here. And so you can see a k to the nth power for small k will be a really small number, and I want 1 minus k to be as close to 1 as possible. That's also why I want k to be a small number. And what we're looking for then is a way for us to take this formulation and come up with a small value for k. So come back here, and this is the derivation. So we go through, I recommend that you walk through this derivation. It's all straightforward. There are no steps in here that you wouldn't be able to follow. And what you find is we want a c, which is -1 divided by some derivative in the interval for the function f. And the result is, if we plug in that c value, if we put that c value in here, we end up with this representation. So let me write this down. I end up with g of x is equal to x minus, and substituting in that c value, I have 1 f prime x naught, and then I have f of x in the numerator. Well, looking at this, what do you see? This is almost Newton's method. I'm dividing, but in this case, I'm dividing by just one slope across the entire interval a to b. And so it's incumbent upon me to try to choose the best slope that I can that makes, because the best slope here is going to make my k value, my bound on the rate of change of g, as small as I can make it. And so there's more discussion about this, along with a couple of important examples that show exactly how I can find a limit for this. So again, walking through the derivation by taking my g, I've defined it the way I need to, I've included the c, then I start taking the derivative and I start looking at bounding what my rate of change is going to be. My rate of change in absolute value must be less than 1. That bound provides for me a range of my c values. In this case, we see the fixed point is between 4 and 5. That's our interval, 4 and 5. And then, since this is our inequality for c, what we end up with then is we are bounded between 0 and -1/5. That doesn't give us necessarily the best answer on what we should choose C to be, but it does tell us the range under the conditions that we know we will be able to find a unique fixed point. There's another example here, which is a follow-on, which basically just says, how do I find perhaps a good value of C? In this case, we've come up with -1/8. But now we can apply the fixed point algorithm to what we have here. So this is a hallmark of the fixed point mechanism for solving these types of problems. We're going to create this formulation, given the fact that we're trying to solve this problem right here. And then we'll create this scenario, but we need to do a little bit of handwork to find the calculation for what the C should be to try to help ourselves out. And then following are some exercises. Before we finish this day up, let me give you an example of what this is going to look like. So here is a fixed point method, and I just want you to be able to see this. I think the pictures really help to explain what's happening. My function is blue. That's my G function. And I'm trying to find a fixed point. I'm trying to find the input value where G, the blue function, is equal to X. So I've drawn a line of G of X equals X right here. So the fixed point lies along this line somewhere. And the way the iterative process works is the following. I pick my initial, in this case purple, my initial approximation. And what I'm going to do is I'm going to feed that in and grab an output, and the output value is right here. But remember, that output value becomes the new input value. So what I'm going to do is reflect it across the line, G of X equals X, back down here, because this is now my new input value. So this is my input value. On the next iteration then, my purple dot will move over here because this is the input. So moving over, here's the new input. So I bring that up. That has an associated output, which is over here. And now we recurse again. So the recursion provides us, here's the output. That gets mapped over to be the next input. And we repeat the process. And so we continue to take the input, generate an output, and that output becomes the next input. And through that process, as long as we meet the conditions, we will end up working our way towards a fixed point. Now, what you'll notice here, the function rate of change near the fixed point is not close to 0. So it takes us several steps in order to be able to move in towards the fixed point. Let me show you a couple of examples that go with the discussion we just had. All right, in this example, I have a similar function. I've just multiplied it by a constant in order to change the rate of change across the interval. And what you'll notice is my rate of change actually exceeds the allowable limit of -1. Remember, my magnitude of rate of change must be less than 1. And let's look at what happens. As we go from input to output and back to input, we end up in a periodic, what we call orbit in dynamics, but we end up in a periodic situation. We're going to be bouncing back and forth off of this function, and we will never move in towards the fixed point. And that's because we are not following the requirements, the hypotheses for the contraction mapping theorem. Let me show you a different example. In this scenario, we have the function multiplied by a c, which makes the rate of change near the fixed point almost equal to 0. And as we run this forward, what we'll see is we very quickly move into the fixed point. So in this case, it's only a few steps and we're at the point where we do not see that magenta dot moving around anymore. So this is our goal. We want to take in a root finding problem, convert it into a fixed point problem, and do so in a manner where we have rapid convergence. Because this is going to give us the best of both worlds. we are guaranteed by the contraction mapping theorem to be able to come up with the fixed point, which is the root to our function f of x. And if we choose c wisely, we can do it in a fast manner. All right, thanks. We'll code this up in class, and I'll talk to you then.